Now let's talk about a function which is something a little more practical than all these simpler things which we've been messing with so far. This is what's called the logistic function. The logistic function is something that can actually model populations and things like that. This is, maybe I should just write down the function first. Just write it down here. The logistic function. And this has some interesting behaviors, as we'll shortly see. First, the function. The logistic function is f of, or you can say p of, it's written like this, p of n plus 1. So p of n plus 1 equals p of n c into p of n into 1 minus p of n, right? Or writing it as an equation, df of x equals c of x, c of x into 1 minus x. Okay, what does this mean? So think about this. This is where c is some constant, right? So think about this. The equation is basically used to model populations and things like that. So let's just look at this. This basically says that the number of and a few things up front before I just describe it. So usually you have some kind of physical limitation on the population. So let's say there's a maximum number of individuals or units that can exist in the space or something like that. There's some physical limit on the absolute maximum number, and p is expressed as a percentage between 0 and 1 of that maximum. So this basically means that the population at generation n plus 1 will be c multiplied by the population at generation n multiplied by 1 minus the population at generation n. And c is what we call the ecological constant. This is something which is determined from various atmospheric conditions, amount of food and conditions like that that describe the environment in which the population exists. Okay, c is often chosen between 1 and 4, right? And so it has interesting properties. It affects the behavior of this in interesting ways. So we'll just see all that right now. Now think about this. Suppose the population is 0, right? And it'll stay 0. So if I were to just write this out, let's just call it def logistic, and we give it x. It would, and let's see, logistic. Let's just write iterate lambda x, right? And let's give x as c as 1 into x into 1 minus x. 1 minus x, right? And iterate this 10 times, starting. It start from 0 and iterate it 10 times. Sorry, I forgot to start here. So if the initial population was 0, then this x would be 0, and so it will stay as 0 forever, right? Because there's no populations, no individuals to actually reproduce and create the next generation. If the initial population were 1, then it's overcrowded. Next thing, everyone would die and we get 0. So 1 is eventually fixed. Right? 0 is fixed. If the population were very, very small, 0.0001, right? It would grow slowly. If the population were very high, it would start reducing, right? And it would reach some kind of equilibrium. So while it's simplistic and it doesn't really describe a large population, but it still has various characteristics which we can use for our study, and we'll do that right now. The interesting part of this equation is this c which we talked about. In this case, we've set it to 1. This has interesting properties. So let's look at this. Right? Let's just take a value of c and behavior of this. Just try to write this down, see what we get. Now let's just try this. So suppose I have, let's take C as 0.5. Okay. C is 0.5, and I'm going to start with this, let's say 100 iterations. It's becoming very, very small, and this, it seems to be like 0.8, 0. Let's see, if you try small ones, everything, no matter what, it seems to tend towards 0. Right? So we just say that. So Z is 0.5, all orbits tend to 0. What about when C is something a little bit bigger? Let's increase it just a little bit. Well, that's no difference here. 2, 3, 4, 7, 8, and 9. This also 0.8. All of this tend to 0. Let's change it. Let's increase it to 1. As we did earlier. Now over here, what happens is you start something. It doesn't move as fast. So in the other case, like by 100, we had already reached like an infinitesimally small number, multiplied by 10 raised to minus 11 and things like that. This thing, it stays this way. If I have to actually get it down there, I have to increase the number of iterations substantially. Right? So even after 100,000 iterations, it's still at 10 raised to minus 6. And on the other case, it reaches there within 100 iterations. So it is tending to 0, but a lot more slowly than the earlier case. Right? This doesn't even get there. It just plays around over there. So with 1, all orbits tend to 0, but slowly. Okay. I'm not checking the other orbits. You just have to take my word for it, or you can take this program yourself and try it out. It's simple enough to do. Now let's try something else. Let's increase this to 1.5. Let's see what happens there. So with 1.5, things tend to 1 by 3. So if it's 1.5, all orbits tend to 1 by 3. Right? What if it's 2? Well, this tends to 0.5. At 2, all orbits tend to 0.5. That's half. And interestingly, at 3, you can see that all orbits tend to it gets to 2 by 3 actually. But the thing is, you have to iterate a sufficient number of times to actually get there. Goes there. You can see it slowly oscillates around 0.66666. A bit less, bit more, bit less, bit more. And it goes around there and finally converges to 0.6666. You can increase this as much as you want. So with 3, all orbits tend to 2 by 3, but slowly, and oscillate around. So that's the behavior over there. Let's try another one. Let's try 3.2. Now we've gone above 3. Right? Let's check the iterations. Well, this is interesting. You can see that it's 0.5, 799, 0.5, 799, 0.5, 799. It's cycling between. So if I get 3.2, you have a period period 2 cycle, which is 0.51, and 0.799. Now let's increase this a little bit, 3.5, and see what happens. Just a little bit. So you can see how the just this logistic equation, I initially started off by saying it's simple, but you can see how the ecological constant affects what will happen to this population, right? So you can see right now it's 82388750, 82388750. So this is actually a cycle of period 4. Right? This cycle repeats again and again. So if I were to do this, I'll just take these things down so that we can use it later. Period 4 cycle. Yes. Alright, so now what? Let's move on. If we increase it a little bit more, just a little bit more, 0.55, so I'm increasing this by 0.05. Right? Now what happens? Let's just make it a little bit more. So you can see as we reach for, the behavior starts becoming more and more complicated. Just try with this. Now it's more interesting. 823788548135. Right? Oh, sorry. So if you just take this much. So 823788. You can see over here that it approaches an 8, 2, 5, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so this is a period 8 cycle. Right. You can see after this, after this we get back to the 827, 370, 881, 540, 812, 354, 887, 506, and goes back to the 827. Right. So this is actually 1, 2, 3, 4, 5, 6, 7, 8 period cycle. Right. So we can write this down. So period 8 cycle. Okay. Let's get these numbers over here so that we can use it later. Eight, 2, 8, 8. Maybe we'll just keep one more. Okay. Right. So these are the remaining ones. These are the values in the period 8 cycle. Keep them here. Now let's increase it a little bit more. Let's say we go to 4, which was what I mentioned, like the edge thing. This is interesting because it goes completely out of control. 371002, etc., etc., etc. There is no pattern. It looks like as if it's completely out of control. Okay. Some initial points have very simple orbits, like for example, if you take 0.5, it's very simple. It just goes to 0. It starts off at 1. Just iterate it just 10 times. You can see it starts off at 1. I mean 0.5 goes to 1, and then after that it just says it's 0. But anything else, even if you change this thing slightly, it just goes completely out of control. You don't know what's happening. The numbers are like completely out of whack. Left, right. There's no pattern. There are no cycles. There are no periods. There's nothing. Right? You don't have to even go this much. You just have to take just a little bit, and you can already see that the behavior is gone just by increasing 001. All right. So this with 4, there is no pattern. Right. With you go beyond that. Let's just take 5, right? And let's take this 0.5 or something. It goes to infinity after a while, perhaps. Yeah. So there's just 9, 10 iterations. It goes to infinity. So with 0.1, it goes to infinity. With 0.2, it goes to infinity. With 0.5, you already saw it. With 0.8, 0.9. With 0, stays at 0. It's a fixed point. But you can see that most numbers, it tends to infinity. With 5, orbits tend to infinity. So this is the behavior of our function with different values of c. Right? We have fixed points, a few periodic points. We have no patterns. We have everything tending to infinity, all sorts of things just by changing the value of one constant. So this is the problem with nonlinear functions. It's unpredictable what they do. And what we're going to try is to try to make sense of this. So in the next segment, we'll talk about how we can visualize this rather than just use a simple program like this to see what's going on.